So before we begin our discussion today of how we force the metric to be spherically symmetric, that is, how we impose this notion of spherical symmetry on our problem, I want to just cover one thing I left unsaid in the last lesson. We left that lesson with this idea of how to calculate the line element through this simple equation where this is the parameterization of the world line in space-time. T is the parameter along that world line, which is often called the proper time. That's how we'll often use it. And of course, this is the metric. But now consider the metric that I prefer to use, just a preference based on the way I learned it. It has no preference because I claim it's superior. It's just we prefer what we're familiar with. This is the metric I'm familiar with using when studying general relativity. And it has this negative sign with the time associated with the time coordinates. So this would be time x, y, z. And this is obviously the Minkowski metric, which means basically flat space-time, right? And it's Cartesian, which means the name of the coordinate system is Cartesian. It's a Cartesian coordinate system, right? It's an orthogonal rectilinear coordinate system. And when you use this convention where the negative sign is floating along the time variable, then what will happen is all of your world lines, your physically realizable world lines, which are all time-like, right? All physically realizable world lines are time-like. What that means is that the length, the distance along this will be actually will be negative, right? These distances will be negative. Or I guess the way I should say it, the dominant terms, when you execute this sum, you'll get a number that's less than 1 for every term because it'll just work out that way because it's a time-like path which is going to end up having this less than 0 problem. So that, of course, creates a problem with the square root. So in this convention, you have a minus sign there, and you'll see that in many textbooks. You see this minus sign in there, or occasionally you'll see an absolute value in there. But when you use this convention, you will end up having a minus sign in this expression for the line element. When you use the opposite convention, you don't have that problem, and they just leave it this way. Okay, that's just a final point. Now, this is the metric in Cartesian coordinates. So today, to begin our topic today, where we force the metric to be spherically symmetric, we have to think about the flat metric, the flat Minkowski metric in spherical coordinates. And the reason we need to do this is because the solutions we seek are going to have boundary conditions. And in this particular problem, if this is our center of our coordinate system, where we presume the center of symmetry, we want to know that whatever the solution is, we imagine that farther and farther away we get, when we get way far away, space-time is flat, right? We're assuming asymptotic flatness. This is called asymptotic flatness. So far, far away, and we don't know what far means yet, right? We don't quite know what far means, but whatever far means, it better mean, one of the ways of defining far is that space-time in whatever place is far is going to be asymptotically flat. Now we know what a flat space-time looks like in spherical coordinates because we've gone to the catalog of space-times. And the catalog of space-times tells us what Minkowski space in spherical coordinates looks like. So Minkowski means flat, and which is essentially no gravity at all, no gravitating matter. And spherical coordinates is just the method we're going to use to evaluate, to label points in space-time. So the spherical coordinate system here is, time is called a t in the catalog, the radial distance they call r, the polar angle they call theta, and the azimuthal angle they call phi. And the boundaries of these things are pretty clear. Phi goes from 0 to 2 pi. The polar angle goes from 0 to pi. R is always a positive real number, and t can be any real number, right? So those are all very important little facts. And in spherical coordinates, the flat space-time metric is this object, and we know that from this that this must be the way to calculate line intervals when we are dealing with places that are far away from the center of symmetry of our gravitating system. So we're going to have a gravitating system that's spherically symmetrical, and the requirement we impose on that is that the boundary condition, the asymptotic condition, is that it must be flat, far away from the center of symmetry. So here in the catalog of spacetimes, this is the catalog, and I think I have a reference for how to get this catalog in the show notes. But in the catalog of spacetime, we have the flat Minkowski metric, and we have it in spherical coordinates. So this is something that we just need to understand to start with, that a coordinate transformation from Cartesian to spherical coordinates in Minkowski spacetime will take the metric that goes minus dt squared plus dx squared plus dy squared plus dz squared. It will take that and give you this in the coordinate system where g equals c equals 1. So this c squared is just a 1 in our coordinate system. And from this we extract the metric components, which is going to be minus 1, g00 equals minus 1, g11 will equal 1, g22 will equal r squared, and g33 will equal r squared sine squared theta. Now in the notation of the catalog, of course, g00 is actually gtt, g22 is g theta theta, g33 is g phi phi, and g11 is grr. And I'm going to kind of move between these two notations, but that is the metric components in this system. Now, the catalog also gives you the Christoffel symbols in this system, and we should be able to calculate those things. And just as a quick example, let's calculate this one here. But first, let's review a few of the quick points about spherical symmetry that we have to understand. This is our blown up version of the of this line element here, and we want to understand, first of all, why does this thing need to be diagonal, right? Why does a spherically symmetric spacetime need to be diagonal? And if we understand that, say, x3 corresponds to the phi variable and x2 corresponds to the theta variable, we know that the line element, right, this thing, this ds squared, this line element, it really shouldn't matter if you move a little bit in the positive direction or in the negative direction. So if d phi is greater than 0, you'll generate a little line element everywhere you see in this case, D3, right? So here you'll see one, here you'll see one. Anywhere here there's a D3, here, here, and here. So anywhere you see that, you'll have a little positive factor in the contribution of that term. So if dx3 is greater than 0, that is a positive factor contributing to this term. But you know that if you went the other way, right, if instead of d phi being a little bit, well, that's the phi angle, but imagine you move a little bit in a positive d phi. If you went the other way, the length of that line element really shouldn't be any different. So even if d phi is less than 0, the line element's length shouldn't change. But notice, if you change the sign of just d phi, the sign of this term would change. Likewise, the sign of this term would change, and this term would change. Now, if we think about it in terms of regular our geometry, in order for those terms not to change sign, they basically have to be 0. And so we immediately eliminate the spatial terms that would change sign with a change of sign of dx3. Now notice this one does not change. dx3 squared does not change, so we leave that one alone. But dx1, dx3, dx1, dx3, dx3, dx2, dx2, dx3, those go away. The same is true for the theta term, for x2, so we have to get rid of those as well. dx2, dx1, dx2, dx1, we leave that one alone. I guess it's just those two. So now, on the other hand, it's not completely clear that that would be true for the time direction. In other words, if you change this theta variable, or if you change one of the angular variables, what about this time piece? But with a little thought, I think you'll realize, no, the time ones shouldn't change sign either. It doesn't matter. We're all moving forward in time. It doesn't matter if you do a little bit of a swing to the left or the right. Your path in space-time should definitely be the same. So we're going to get rid of the dx03, the dx02s, and these two as well. So that leaves us with these guys, the diagonal terms, and then the dx1, dx0 pieces, right? And the reason the dx1s don't have the same logic affixed to them is because our understanding of spherical symmetry has to do with measurements of things on a sphere, and that sphere presumes a certain value of r. If you change spheres, all bets are off. It could very well be that the lines placed on this other sphere are going to have totally different measurements, because spherical symmetry only means that it's independent of the angular variables, not the radial variable. So those guys, we can't just wipe those away. So spherical symmetry, though, does demand that the only surviving terms are going to be G alpha alpha, that's all the diagonal terms, and then G01 and G10, right? The two radial terms. So those terms will be non-zero by virtue of spherical. Spherical symmetry does not eliminate those two terms. So now we can write down our most general metric so far. I mean, general metric including the spherical symmetry stuff we just calculated. So to show how these diagonal terms between T and R can always be eliminated, I've written down the most general matrix element, or the most general matrix element, that's not what I meant, the most general line element in this suggestive form. Now, all of these capital letters are meant to be understood as functions of time and radius only. So there are some unknown functions of time and radius. And for example, the unknown function that appears as the metric component in dt squared, I call f. We have to throw a negative sign because our signature is such that it's a negative sign up front. I'll talk about that negative sign a little bit more in a moment. There's other ways of enforcing a negative sign there. But the f squared is going to be positive. I want that to be for this analysis. So I need that negative sign up front. And likewise, there's an h squared on the dr term, and that's also that's an arbitrary function of time and radius. It's just called h. And whatever that h is, there's going to be some function in front of the dt dr term, some metric component there as well. But whatever that h is, we just factor it out. And so we factor out a 2h from whatever that function is. So for example, that might have been called w. Well, we factor out the 2h, and what's left behind we call g. And we're doing this for a reason, because I want to show you that you could always do it, by the way. Whatever this function is here, whatever this guy is here, you factor 2 times its square root out of whatever is in front of here, and then whatever's in front of here you just call f squared. And then you make the following rescaling of the radial variable. You call b dr prime squared equal to g, this thing, plus h dr. And that squared term, if you square that out, is g squared dt squared 2hg dt dr plus h squared dt dr. And if you make that substitution into this expression, what ends up happening is you find that this squared term is actually equal to that and that plus g squared dt squared. So you end up with a g squared dt squared and a minus f squared dt squared. And so if you redefine a, which is going to be the leading function in front of dt prime, as g squared plus f squared, you end up seeing that this will all now cancel, because what will happen is it's got to be minus a, so you'll have a minus gt squared minus f squared. That minus g squared will cancel with that g squared, and it'll leave the f squared behind, and everything kind of cleans up. And this rescaling then eliminates this middle term, because you've now replaced it with, you've replaced it with dr squared, dt prime squared. This is dr prime squared. You've simply rescaled the radial coordinate, and by rescaling the radial coordinate, you've eliminated this cross term. And you can always do this. There's a way of doing it also to rescale the time coordinate in the opposite signature, but it's guaranteed to be doable every single time. And because of that, we can always presume that our spherically symmetric line element does not contain this cross term, because if it does, you just simply rescale the radial coordinate to make it go away. So once that's done, you end up with this line element, right, where a, b, c, and d are all functions of time and radius only. And then you look at these two guys here and you say to yourself, well, imagine that we're in our coordinate system with, say, this is just an easy way to think of it, theta equals pi over 2. If that's the case, then you're dealing with, and I'll kind of draw it out here, you're dealing with a point that's in the plane. This would be the z-axis, x-axis, y-axis. Here's your pi over 2 point. I'll make it green. It's the polar angle of pi over 2, and it has some unknown angle phi, but we don't care what phi is. So now you imagine that you swing it to the left or right a little bit by d phi, and it should create a little arc segment. But also, if you swing it up and down by d theta, you should create another arc segment, and d phi and d theta should both give you the same arc length. So the only way that can really be for that case is if c and d are the same. Otherwise, a small change in d theta will give you r squared, and a small change in d phi will give you r squared times d, which could be different than c, right? Now, sine squared theta, that's equal to 1 in the circumstance we've designed here. So in order for those arc lengths to be the same, c has to equal d. And ultimately, that leaves us with this expression. Let me clean up my c r squared a little bit. This is our expression for the most general line element in a spherically symmetric coordinate system. It's this term here is our solid angle element, and that's the only place any of the angular variables are allowed to show up. The radius we factor out of c here to just as a reminder, because it makes us remember that we're dealing with that spherical element from Euclidean space. Ultimately, when in the large radial distances, this c has to go to 1. And all that will be left will be r squared and times this this element here, which we usually call d omega squared. And then we have some unknown function of time and radius in front of the radial variable, which I'm now calling rho. We've rescaled r a couple times, but I like to call it the unknown variable rho, because I don't like, if people are too, it's too easy to think of, if you leave it as r0 minus r1 is some kind of real distance. And it's not, unless you specifically create your coordinate system so that the difference in radial variable or radial coordinates actually equals the metric distance between 2 points. That's not the case, and I'll show you how you actually do that in a moment. But so I renamed the radial variable rho, and then of course there's the time variable, and I have a minus a there, but that's kind of silly because a, if it's an arbitrary function, a function we don't know, could be positive or negative, right? So in some sense, it's a little bit beside the point to enforce the signature that way. Somehow, though, a has to always be negative. And one of the ways that's typically done is to write it as e to the a, right, where there's some function a, and that'll always keep it positive, and then you throw down that negative sign. Likewise, this would be e to the b to keep it positive, and e to the c to keep it positive. Notice how all the r squared will always be positive and the sine squared will always be positive. So that's another thing you'll see out there quite a bit. But for right now, the method I'm going to use is just I'm going to assert that a is a positive function, and I'm going to enforce it with a little negative sign right there. All right, so now we're looking at this as our general line element. And from this, we're going to make a few choices. The first thing we must understand is when we are thinking about something that's very far away from the center of symmetry, this term, and this term had better go to 1, leaving behind just the Minkowski metric in spherically symmetric spacetime. But now we can kind of choose to understand what is it that we want our coordinate system to do. And let us consider, for example, measuring the length of a line, a space-time line, on the surface of a sphere. Let me draw that sphere. On the surface of a sphere, and we're going to come up with some line on that surface of the sphere. We're going to measure the length of that line, but we're going to do it at one instance in time, so t equals t0, and for one specific radial distance, r, or rho, I guess is what I'm calling it now, rho equals rho 0. And there's going to be no variation in time and no variation in rho. So when we measure this, we're going to not be dealing with this term or with this term, because dt and dr are going to be 0. We are, however, going to allow theta to and phi to shift around. So how would we measure such a thing? So we would write the line element in this form now, right? We want just a little segment of line element. This always gives us the solid, sort of the square segment, but we need to take the square root of both sides, which is really kind of weird because it doesn't really, this is nothing you can actually deal with in calculus. The way you have to understand this, of course, is we know the world line, and I've said this before in the other lecture. The world line is some function of some parameter tau. So we supposedly know these two functions. If we're going to measure the length along a world line, presumably the world line is given. And the way you have a world line given is you know the coordinate theta is a function of some parameter tau, and you know the coordinate phi is some parameter, function of a parameter tau, the same parameter. So d theta d tau equals d theta, and the convention, the notational convention that gets us out of this mess is this part here, d theta d tau, we can calculate, because if we know the function, you just take its derivative with respect to tau. Then you're looking for this guy squared, which is this whole thing squared. So that's ultimately going to be d theta d tau, which is a function, squared, d tau squared, and then we're going to take that d tau squared and just pull it out of the radical altogether. Right? So I guess you would have that just to make sure that d tau does not show up in the radical. And so once you've done that, a finite distance s is just going to equal this guy, which is just going to equal the integral of that d tau. This here is a function, none of those are functions of tau, so that comes out front. So you have r times the square root of this function c. I'm no longer writing function c as a function of time and radius, right? It's just understood, right? I'm not going to, it gets messy if I do that. And then it's the integral of basically this whole thing right here goes right there. Now what's important about this is this piece here is exactly what you would get in regular calculus, Euclidean space, flat space-time, if you're just calculating the distance of the length of a line on the surface of a sphere, if you know the parameterization of the line, as long as it's constrained to the surface of the sphere. So that's the answer you would get in normal solid geometry, calculus and solid geometry. You can go to a calculus book, you'll probably find this very expression somewhere in that calculus book. So the only difference is this thing up front. Oops, actually, let me make a quick correction there. This r right, r, so square root of c, this is the part you would find in a normal calculus book. That r gets sort of sucked in there. But the point being is that the difference is this square root of c part. And so the way you handle, so what we could say is if c was equal to 1, then you would get the same answer in this metric here for distances measured on the surface of a sphere, if you just set c equal to 1. So can you set c equal to 1? And the answer is yes. You just create a new variable, and I keep playing around with these variables. I meant to call this rho, right? Rho. Rho. This should be a rho. This should be a rho squared. I'm just changing the name. I like to keep rho because I want to emphasize it's really not the same as the radius variable. But if we imagine that we set a new variable, rho prime, that was equal to the square root of c times rho, then you actually would have a solution, or once you made this change of variables in this metric, or this coordinate system, then it will turn out that this part up here just ends up being rho prime, which is exactly the Euclidean answer, or I should say the flat space answer. So no matter what c is, we can always make this change, right? And if we make that change and we execute it, which we can do arbitrarily, right? I mean, this is the most general metric, but we are always allowed to make that change, that simple coordinate change. If we do that, then c will always be set to 1. Now that doesn't change a or b, or that it doesn't, it changes, because remember, a is a function of rho and b is a function of rho. So if you change to rho prime, you're going to change the functions a, b to some other functions, a hat, b hat. But whenever you do, you will end up always with c equaling 1 in that circumstance. Or this, I guess what I should say is this leading term will just equal rho. And then your most general metric under that condition will be this expression here. You'll have some unknown coordinate function a and b, which will be different than the previous ones because we've changed the variable rho. And you'll end up with this term here, rho prime d theta, and then this the solid angle piece. Now, rho has been rescaled, so what's interesting is it's not going to represent the distance to the center. However, if you integrate over a sphere at a certain value of rho, the area, the surface area of that sphere will be 4 pi rho squared. So the surface area of every sphere at a coordinate distance rho will be exactly what you expect. The price you pay is that the distance to the center, which would be imagine moving along a radial line from the center of symmetry in, right? So d rho is less than 0. You're going inside, and then these guys here are all constant, so they go away. So what will that distance be? Well, that distance will be ds equals the integral from rho 1 to rho 2 of b t rho d rho. But this does not equal rho 2 minus rho 1. In other words, the distance, well, actually that's not ds, that's fully s, right? That distance, that radial distance between two radii measured through that true actual length, which is determined by the metric, right? The metric tells us how far apart things are. It's not equal to simply the distance between the two radial coordinates anymore. It's off by this factor of b, right? So by forcing spheres to have the correct surface area for the radial coordinate and for lines on those spheres to have the expected length on the radial coordinate, the price we pay is that the radial coordinate doesn't actually measure the distance to the center. Now, we could have taken the opposite approach. We could have forced b equal to 1 by rescaling some coordinates. And then we would have had the problem that distances on the spheres would have been different than you might expect. There's always something that has to give here. The choice that we're going to make is the one that we've worked out, right? We're going to make this choice. And that choice is called Schwarzschild coordinates. Schwarzschild coordinates are set so that spheres, activity that happens on spheres, is undistorted. And then there's other choices. There's isotropic coordinates, there's Gaussian coordinates, there's free-fall coordinates. But the one we're going to be interested in is Schwarzschild coordinates, because that's the most famous one. I don't know if it was the first one discovered necessarily. I think it was the first one discovered, the first one used. But regardless, it is the most convenient one to understand. And the point about that is that now we've arrived at our spherically symmetric metric. It's spherically symmetric, and we've only made choices that we're always allowed to make, so this is still quite arbitrary. But the coordinate system we're choosing forces all of the unknown metric components into these two functions. A, which is a function of time and radius, b, which is a function of time and radius, and Schwarzschild radius, which I indicate by a p. Those are the only two unknowns in the metric itself. Everything else, this is all just pure coordinates, right? It's the function of those coordinates throughout space-time that we need to know about. And notice theta and phi are not part of A and B due to spherical symmetry. If it was, then you would be measuring weird things. As you move through time, it would depend where you were on the sphere. As you moved radially, it would depend where you were on the sphere. And that's not spherical symmetry. So we've reduced the metric to this kind of expression. Let's see. We've got gtt, which is g00, minus some unknown function of time and radius. We have g rho rho, which is g11, some unknown function of time and radius. We have g phi phi, which is g22, which is rho squared, and g theta theta, which is g22, which is rho squared. And you can see, because that's the leading coefficient of d squared, and g phi phi, which is g33, which is sine squared theta rho squared. This sine squared theta appears in this problem. Even though it's spherically symmetric, you still have an angular dependence on this, this metric component. There was a time where I thought that that wasn't the case. You would never have an angular dependence. But this is an artifact of the fact that you can choose arbitrarily where to plant your z-axis. And that choice actually does matter in the component. In order to keep the distances the same, you have to sort of understand where you've planted your z-axis. And that's kind of manifested in this sine squared rho squared. And that's it. That's the most general spherically symmetric metric in Schwarzschild coordinates. And when I say Schwarzschild coordinates, I mean that any sphere is always going to have the surface area equal to its radius squared, 4 pi r, this would be 4 pi r squared, will always be the surface area of a sphere in that coordinate system. And of course, radial distances now are no longer trustworthy as measurements of yardsticks from the center of symmetry. Okay, so that is the answer to the question about how we force our metric to be spherically symmetric. We force it to be spherically symmetric by demanding it have this structure right here. The spherical symmetry already solves a lot of the metric. It tells us what g phi phi is. It tells us what g theta theta is. It tells us what all the mixed terms are. It only doesn't tell us what g00 is. A has to be positive. And what g rho rho is, where b also has to be positive. So to summarize, this is our final answer on the spherically symmetric metric. And this is actually meant to be a negative sign here in front of this A. It doesn't quite look like it because of all of these blanks. That's a negative sign on the A. And And that's what we're going to work with. Now, the reciprocal metric, or I shouldn't call it the reciprocal metric, the contravariant components of the metric G mu nu are just going to be the reciprocal values of these guys: 1 over A, 1 over B, 1 over rho squared, and 1 over rho squared sine squared theta. This line here is not meant to be a negative sign. I wrote lines instead of zeros, but all of these guys are actually these are missing spots. There is no G T phi, right? So I put a little line there. So these red ones are the contravariant components, and these are the covariant components. And the reason they're straight up reciprocals is because G mu nu G nu beta is delta mu beta, right? So when you have a purely diagonal metric, you'll see that sum forces this simple relationship between the contravariant and the covariant styles, or contravariant and covariant components. So once we have this, now we can start calculating everything else, and that's what we'll begin doing in our next lecture. For example, I need to be able to do things like this in order to calculate my Christoffel symbols, right? I need to be able to calculate these objects. And so, well, that's easy, right? I could just say G T with respect to theta, well, that equals 0, right? Because I know GT is not a function of theta. But I can say GTT as a function of t, well, that's going to be minus a dot, where dot would be a derivative with respect to time. I could say GTT derivative with respect to rho is minus a prime, where prime is the derivative with respect to rho. See, as I now know the form, this arbitrary function, whatever that is, I can still calculate these derivatives. I calculate all these derivatives, and I can get the Christoffel symbols in terms of these two unknown functions A and B. Those Christoffel symbols will ultimately give me the curvature, which ultimately gets put into the Einstein equation, and then we churn and churn until we actually solve for A and B. So we'll begin that process next time. Oh, I did mention that I was going to show how there's another form of notation, right? Instead of saying minus A dt squared plus b dr squared, and then insisting that A and B be positive, often it's written this way: minus e to the 2a, and then plus e to the 2b, and this would be dt squared dr squared, where the 2 sort of makes it something that's easily squared. This enforces that positive condition, and yet this will be still a very arbitrary function. Just ends up that the relationship between this A here, which I've asserted to be positive, and this B, which I assert to be positive, is obviously logarithmically related to that thing. You'll see this very, very common in textbooks. And when I first saw it, when I started studying this, it was very confusing, because all of a sudden I'm seeing, assume this is e to the 2a, and I never quite understood, well, why would you assume that particular function form? And what I didn't appreciate is that e to the 2a, where a is an arbitrary function, this is still just an arbitrary function. The only thing is it's forced to be positive, right? Regardless of the sign of a, or regardless of any restriction on a. So in some sense, a can be truly arbitrary, and this makes it positive. In our case, a can't be truly arbitrary. It's got to be positive. So that is a distinction you'll see in a lot of textbooks. Okay, see you next time.